In a famous James Bond movie, the imposter British agent was spotted by ordering red wine with fish. Worse still, but not shown in the movie, this same imposter ordered a martini with an ice cube instead of an olive. After drinking the martini, the imposter swirled the ice cube, uniform circular motion, in a circle of radius r equals 0.02 meters, as shown in the figure below. The mass of the ice cube is 0.02 kilograms. Circular motion is a force problem, and the first step in every force problem is to draw a free body diagram. This dot will represent the ice cube. The first force we imagine on the ice cube is gravity, 0.02 times g. In addition to gravity, the ice cube is against the side of the martini glass and therefore experiences a contact force. Contact forces always supply a normal force, where normal is the mathematician's word for perpendicular, and they sometimes supply a frictional force. In this case, since we have an ice cube on glass, we neglect the frictional force. These are the only two forces in our free body diagram. The free body diagram is 2 dimensions, and so we choose the usual convention for aligning the coordinate system, and that is with the acceleration. The ice cube may be moving in a constant speed, but since it is moving in a circle, it continually changes direction, which is a change in velocity indicating that there is an acceleration. And we know that whenever an object moves in a circle, the acceleration is directed toward the center of the circle. Given that this picture represents the ice cube on the left-hand side of the glass, this direction to the right is positive, and we give it the name centripetal. To complete our coordinate system, we need the other axis to be perpendicular to this one, and that one will be vertical. We're almost ready to create equations from this free body diagram. However, what we notice is that even though the gravity force of 0.02 g is directly along one of the coordinates, the normal force is split between the centripetal and the vertical coordinate. This means that we should break it into 2 components. We make these components by following one of the axes until completing the triangle follows the other axis. Now our only challenge is to get the 60 degrees given in the problem itself to be located somewhere within this triangle. What we recognize about the 60 degrees is that this is the angle between the horizontal and the side of the glass. We do have an axis which is horizontal, we've named it centripetal, but we don't have anything parallel to the side of the glass. And so what we do is we simply add that side, and we recognize that if this angle is 60, then that one is 30, and if that angle is 30, this one is 60. This means that the 2 sides of the normal force can be written thusly. N cos 60 is the side adjacent to the 60 degree angle, and N sine 60 is the side opposite to the 60 degree angle. This free body diagram will yield 2 equations, one in the vertical, the other in the centripetal. Let's begin with the vertical. Because there's no acceleration in the vertical direction, we haven't chosen one of the directions to be positive. We'll choose up just because that seems more natural, meaning that the force in the plus direction is n times the cosine of 60. The force in the minus direction is m times g, and the sum of the forces is m times a, where the acceleration is 0. This equation has only one unknown, the normal force, which gives the numerical result 0.392 newtons. The only remaining task in this problem is to analyze the centripetal direction. Looking back at the free body diagram, we see that the only force in the centripetal direction is one component of the normal force, n sine of 60, and so for that reason the centripetal equation will be simple as follows. The sum of the forces in the centripetal direction is equal to m times the acceleration in the centripetal direction. The question we ask ourselves is that since this is constant speed motion, is there an acceleration in the centripetal direction? And that question always has the same answer. Yes, there is an acceleration in the centripetal direction, so that the ma term is the mass of 0.02 times v squared over the radius. Since we solved for the normal force in the previous part of the problem, and the radius has been given as 0.02 meters, we get the following expression for the velocity, which yields the numerical result 0.58 meter per second.